For decades, almost every solar panel you have seen has been based on the same material, silicon. Silicon works well, it is abundant, and manufacturers learned how to make it reliably at large scale. But silicon has a built-in ceiling. Silicon cannot convert more than a certain fraction of incoming sunlight into electricity, no matter how perfect the manufacturing gets. Tandem panels have demonstrated efficiencies approaching 30% in large area cells, not just tiny laboratory samples, which is far beyond what silicon alone can reach. Engineers kept pushing closer to the silicon ceiling, year after year, by refining processes and reducing defects, but each improvement delivered only very small gains. Eventually, those gains became harder and more expensive to achieve. Perovskite silicon tandem solar panels exist because engineers needed a way to move past that limit without discarding the entire silicon manufacturing base. A tandem solar cell works by stacking two different light-absorbing layers on top of each other. Each layer is tuned to capture a different portion of sunlight. Silicon is very good at absorbing lower energy light, especially toward the red and infrared part of the spectrum. Perovskites are adjustable materials that can be tuned to absorb higher energy light that silicon wastes. When sunlight hits a tandem cell, the perovskite layer absorbs the high-energy photons first, and the remaining light passes through to the silicon layer underneath. Instead of forcing one material to handle all wavelengths imperfectly, the tandem structure lets each layer focus on the light it can convert most efficiently. The word perovskite does not describe a single chemical substance. It describes a crystal structure. The name comes from a naturally occurring mineral identified in the 19th century, which was named after the Russian mineralogist Lev Perovsky. What mattered about that mineral was not its chemistry, but the way its atoms were arranged. That same atomic arrangement can be recreated using many different combinations of elements, which is why modern perovskites are really a family of materials rather than one specific compound. This crystal structure makes it unusually easy to tune how the material interacts with light. By slightly changing the composition, engineers can adjust which wavelengths are absorbed and which pass through. That tunability is the core reason perovskites work so well as a top layer in tandem solar cells. Please subscribe. Researchers have studied perovskite materials for more than a decade because they absorb light extremely well and can be made using relatively simple processes. The problem was stability. Early perovskite cells degraded quickly when exposed to moisture, heat, or ultraviolet light. Some perovskite cells failed in weeks or months. Other perovskite cells lost efficiency steadily, even under controlled conditions. That behavior made perovskite cells unsuitable for real panels expected to operate outdoors for decades. The material could perform exceptionally in short tests, but it could not survive the conditions required for long-term use. The turning point came when researchers stopped treating perovskites as full replacements and instead treated perovskites as additional layers. By placing a thin perovskite layer on top of a conventional silicon cell, engineers could keep silicon's durability while gaining the efficiency boost that layer provides. This approach also allowed the use of low-temperature deposition techniques that do not damage the silicon layer beneath. That manufacturing constraint matters because silicon manufacturing lines already exist worldwide, and replacing those manufacturing lines would require massive investment. Adding a layer on top of an existing silicon process is far more practical than rebuilding factories from scratch. Manufacturing is where many promising technologies struggle, and tandem cells are no exception. Perovskite layers must be uniform, defect-free, and consistently bonded to the silicon layer below. Even small imperfections in the perovskite layer can create electrical losses or lead to early degradation. Engineers also had to deal with ion movement inside perovskite materials, which can slowly reduce performance over time. This behavior made sealing the layered structure essential. Modern tandem cells use multiple protective barrier layers that block moisture and oxygen while shielding the active materials from heat and ultraviolet light. Standard silicon panels commonly operate in the low 20% range. That efficiency difference allows more power to be generated from the same physical area. In locations where space is limited, higher efficiency directly changes what is possible. Higher efficiency also reduces the amount of supporting structure needed per unit of output, which influences system design choices rather than just performance metrics. Efficiency alone does not guarantee adoption. Tandem panels introduce new ways they can fail. If the perovskite layer degrades faster than the silicon layer, overall panel performance declines, even though the silicon layer remains intact. Differences in how the two layers expand and contract with temperature can create mechanical stress. The electrical connection between the perovskite layer and the silicon layer must remain stable for many years. Engineers also must manage small amounts of lead used in many perovskite formulations, ensuring that the lead stays fully contained throughout the panel's lifetime and during disposal. These issues determine whether the panels meet certification standards and long-term warranty requirements. When people talk about tandem solar panels reaching commercial scale, they're not saying that every factory has already switched. Commercial scale means pilot production lines are producing meaningful quantities, certification testing is either underway or complete, and early customers are deploying panels outside controlled demonstrations. A panel that can be produced reliably with fewer defects is more valuable than a panel with higher peak efficiency but inconsistent output. Reliability in production determines whether scaling is practical. Tandem panels will not replace all other panel types at once, and they're most competitive in situations where higher output justifies additional manufacturing complexity. Traditional silicon panels remain easier and cheaper to produce at very large scale. Other thin film technologies fill different niches. The most likely outcome is coexistence rather than sudden replacement. Over time, as yields improve and processes stabilize, tandem designs may become the preferred option in more applications, while older technologies continue in applications where simplicity and cost dominate. There are also limits that tandem cells simply cannot escape. Adding more layers increases manufacturing difficulty and raises the risk of defects. Each interface between layers introduces new opportunities for electrical loss or mechanical failure. As power density increases, managing heat becomes more challenging. Eventually, the added complexity outweighs the benefit of higher efficiency. These limits define how far it can realistically advance, regardless of what might be possible in theory. Perovskite silicon tandem solar panels reflect a change in engineering strategy. Instead of relying on a single material to perform every function, engineers now divide the task across layered materials that share the workload. This layered material approach is harder to design, harder to manufacture, and harder to certify, but it overcomes constraints that single material solutions cannot. Reaching commercial scale means the failure modes are understood, the fixes are effective enough, and the remaining challenges involve refinement rather than fundamental uncertainty. Thank you very much for watching. Please like and subscribe.